Fiery explosions on the moon. Fountains of fires, we call them. How did they come about? We now know the moon and the Earth were major molten objects. How did they cool? How did they evolve? Let's find out. Hi, I'm Jim Green, Chief Scientist at NASA, and this is Gravity Assist. This season is all about the moon. With me today is Dr. Dave Draper, a planetary geologist who specializes in really important stuff like volcanic activity. Dave is the new Deputy Chief Scientist for NASA at NASA headquarters. Now, prior to coming to NASA headquarters, he worked at the Johnson Space Center in Houston, Texas. Dave was the manager of the Astromaterials Research Office, where we house our samples that we bring back from the moon. Welcome, Dave.
Thanks, Jim. It's really great to be here at headquarters.
Today, I want to talk about your unique perspective on what the Apollo program really found out about the moon and the Earth from the samples it brought back. You know, planetary science as we know it today really took off during, but especially after the Apollo program. So what did we learn about the moon that really helped spark this new generation of planetary exploration?
What we've learned, Jim, is that terrestrial geologists had to shed their bias. I mean, we all work on the Earth. We know the Earth. We've been studying it for, centuries, really, as geologists. But every world is different. And when we got to the moon, we quickly realized this is a very different kettle of fish. And when you look at lunar samples, there are a few key fingerprints you can quickly use to demonstrate, hey, these are not from Earth.
Let's go back to the beginning. Let's go back to how the moon was created. What was the moon like way back when that first happened?
Yeah, the giant impact hypothesis says that very early, when the solar system was still in the accretion process, an object about the size that Mars is today, roughly 1/3 the current size of the Earth, collided with the proto-Earth. And that process was cataclysmic and flung material out, and that material eventually coalesced to form the moon. And that coalescence process was really energetic, and in that whole sequence of events, that's what caused the Earth itself to melt. And really, the very, very first samples ever taken on the moon by Neil Armstrong, right after he stepped off the LEM, one of the first jobs was pick something up and get it in a bag just in case you have to bug out quick. And included in that very first scoop of material were little fragments of white stuff that is called anorthosite. Long story short, that led to the idea that the moon must have been completely molten in its very early state. And, I know listeners have seen some of the really dramatic video recently from Hawaii, where they have these huge lava flows flowing down the mountains and, rivers of lava that, covering up villages and all that. We're talking about an entire world that looks like that. So very, very dramatic, very different from today.
So the whole surface was covered in molten rock.
And not just the surface, it went to great depth. In fact, most of the geochemical and experimental evidence suggests that the entire moon was molten, not just the upper layers. So we call this the magma ocean.
So it's starting to collect this material and creates this magma ocean on the moon.
Yeah, that early event had just tremendous amounts of energy. And then additional energy was contributed to the process as all of that material accreted together. All of its gravitational energy is converted into heat, basically, and everything melts. But the really crucial thing is once we knew that the moon had to have been molten, then we had to take the next step. Well, how did that happen? Once we had the idea about the giant impact, we thought, well, geez, what happened to Earth when that happened? And the upshot is that not only was the moon molten, but the Earth was completely melted itself. And that is something we could never have known unless we had gone to the moon.
Well, where does the anorthosite come in? You mentioned right off the bat that, we picked up some anorthosite, and that was sort of a dead giveaway of a molten magma ocean.
Yeah, anorthosite is a rock type. It is made up almost entirely of a single mineral. Minerals are the building blocks of rocks. These are the things that geologists study in detail all the time. The mineral is called a plagioclase feldspar. It's very common on Earth as well, but it's a rare thing to see a rock that is all plagioclase. And what we know is we can very easily measure the density of the minerals. And what we know is that plagioclase is very much less dense than the more what we call mafic minerals that constitute the interior of most terrestrial planets. Plagioclase will float on the magma ocean the way ice floats in your glass of water. And what we inferred, we being the scientific community, inferred was that this plagioclase material must have floated on a liquid that was more dense. That was the primary observation. And just from a couple of small pieces of that puzzle, this whole story could be worked out. But it could never have been worked out unless we had brought back this sequence of samples that each of the missions brought back from all of the targeted landing sites that the Apollo program chose.
Do you think Neil knew the significance of the anorthosite when he picked it up?
No, he sure didn't. He had no idea. But I'll tell you what, Jim, once they brought that material back, it was less than a year before this idea was promulgated that, hey, the moon must have been molten. Of course, Apollo 11 was the first. 12, they already knew where they were going. And 13, they already had those plans before that first material came back. But once they started analyzing that gave them clues about where they should send the last few missions. And in particular, the Apollo 15 mission was chosen to go to a place that, hey, if this idea is true, we ought to be able to find a bunch of that stuff somewhere in this area. And the commander of that mission, astronaut David Scott, really took on board geologic learning, and he went out there and he and his lunar module pilot were looking for this stuff, and they found it. This was one of the greatest times of science hypothesis testing.
So they knew what they were looking for, and they adjusted the location. So this brings her up in my mind right away that, Apollo 13 was going somewhere, and it didn't make it. Was Apollo 14 slated to go there?
Yeah, 14 went to the place that 13 would have gone to.
I see.
So they didn't want to pass up that spot, and then but they adjusted the plan and they sent 15 to where they would hope to find this evidence, and they found the smoking gun.
Well, when we look at the moon today, we see a contrast in gray, if I may say. You see the nice gray, mostly surfaces with impacts in them. And then you see these really dark gray areas on the moon. What are they?
The darkest areas are really widespread lunar lava flows. They're basically what on Earth we would call flood basalts. They're so voluminous that they cover huge areas. The lighter stuff is what we call highlands material. It is made up of different compositions, richer in silicon compared to the dark stuff. And the plagioclase mineral we just talked about is very abundant in these highland materials, and that helps lend it that lighter color.
So that dark gray material we call the mare, that's laying in what we call basins. And those basins are actually impacts that scoured the surface, and this material, this molten rock, flowed into it. So this is different than the magma ocean that we just talked about.
Yeah, the magma ocean, once that cooled off, and it didn't take long. I mean, geologically speaking, a few, maybe tens of millions of years, maybe at most 100 million years for the whole thing to cool off and be solid. That sounds like a long time, but in the geologic terms, that's, about a month of our life. It's not a big long time. That process formed the source regions from which the lavas that came later, that are now on the surface of the moon, formed. So that's the stuff that had to melt to give rise to the lava flows.
So the impacts then that hit the moon that created these basins, and then the molten rock comes up from the interior and starts flowing in these areas. How did it fill these areas, and how did we know how it filled these areas from the samples we brought back?
A common misconception is that those lava flows were in fact triggered by the impacts, but that's actually not the case. The impact basins are themselves, quite a bit older than the lava flows. The lavas came along hundreds of millions of years after the basins formed. The samples contain geochemical fingerprints of how deep they originated and how hot the temperature had to be to get them to the surface. This is the sort of work that I've done in my career. And that helped us understand the sort of dynamic process that had to happen to get that material to the surface.
Well, what then triggered those lava flows to fill in those deep impacts?
We talked a bit about how we have a tidally locked face that faces us.
Yeah.
And we talked about that influence of gravity. Well, that influence of gravity seems to have concentrated on the near side chemical elements that undergo radioactive decay. And when they do that, well, particular potassium, thorium, or elements like this, they generate heat. And when those elements were concentrated together, it generated a lot of heat to help the material get over the hump to start melting. And then that process, it wasn't quite a runaway effect, but it generated a whole lot of magma that could come to the surface.
So the constant tidal heating and dissipation of that energy is keeping that molten rock active, in particular just on the near side of the moon underneath these impact regions. And then it broke through. But it broke through in some ways in a violent way. How did we find out about that?
Yeah, I mentioned that these things look kind of like flood basalts on Earth. If you were to watch a flood basalt eruption, it would look a lot like Hawaii, which is rivers of lava flowing. It's dangerous if you get too close, but it's not going to blow up. But what we're talking about here is things that actually did have explosive eruption styles. Part of the samples that were returned by Apollo were very tiny beads of quenched liquid rock.
So quenching then is when the solidification occurs very quickly and it creates a glass.
It's just like a glass you would make, a hole of water in, but it's made of a different kind of rock than what we make our drinking glasses out of. Glass is the holy grail for people like me who want to study the interior, because we know that material was unmodified from the time it was first melted. The liquid came out, it quenched, nothing else happened to it. So we use these things literally as probes of planetary interiors, just the way we use spacecraft to probe planetary surfaces.
When we talk about these glass beads, how big are they?
Most of these beads are a millimeter in diameter or less. And they're made of, we call them glasses because you can see through them. They're transparent. They have color. A drinking glass that you might have on your shelf, mostly clear glass, but you can make a glass of any color you want depending on what you put into it. And these glasses have chemical elements in them that lend them these colors.
All right, if we accumulated enough of these, could we really melt them all down and make a drinking glass if we wanted to?
You sure could. Get them up there, stick them in an oven, you could make glass just like you would here on Earth, and that would be the coolest glass
It would
ever.
be. It would be. Well, do you think the astronauts were keen to look for these little beads?
Once we recognized, and I believe there were some glass beads returned from each mission. I think when they were first recognized as being very important after the Apollo 12 samples came home. And then, yes, absolutely, they were targeted, but because they're so small, most of them are a millimeter in scale or less, some of them much less. It would be very hard to actually see them. But what they knew by the time they got done with 12 was, okay, this stuff is all out there. And so if you pick up the regolith material from the moon, you're going to get some. However, there's one mission where they really did look hard, and that was the final one, Apollo 17. That was the first one where we had a trained geologist on the crew. That's Dr. Jack Schmidt. And he recognized immediately when he found a special kind of this glass at a place called Shorty Crater that they had found something really important. And when that material came home, he was borne out as being completely correct.
Yeah, I remember that event where he's looking around and he sees these orange things and he talks about them. And there was a great deal of disbelief, is it a reflection off something that is colored that we brought, like the lunar limb and the blankets or whatever it happened to be. But we were far away from all that. And he was out in the middle of nowhere when he found these.
Yeah, that's right. He and Gene Cernan had been riding the lunar rover for a while, and they were kilometers away from their landing craft. And when they first found this, Jack is an igneous petrologist, the same training that I have. And as you pointed out, when you look at the moon, most of it is gray. So to see a vivid color Boy, did that get everyone's attention. And he thought that this was like a hydrothermal vent of the type you might see, say, at Yellowstone National Park. By this time, we had a pretty good idea the samples were pretty dry. There wasn't much water in them, but this said, whoa, maybe this is a water-bearing source. It took time to bring the samples back and analyze them to realize that wasn't true.
Well, that's fantastic. So we found these orange beads, black ones and green ones. What did they tell us about the spectacular events that were occurring in terms of the molten rock filling these craters that are today we call mare?
The main process that forms these beads is something we call fire fountaining. And you can see this in volcanic eruptions on Earth. But on the moon, because of the lower gravity and lack of much of an atmosphere, these things were much more spectacular. They would go tens of kilometers into the sky, and the materials would fall tens of kilometers away from their vent. Whereas on Earth, that's a much smaller thing. If you could have been standing on the surface of Earth at that time and looking up at the moon, you could have seen these things with your eyes.
Wow.
Really would have been something to see.
Now, the color variation also tells us a little bit about where these objects are created in those fire fountains.
Yeah, that's true. What the colors actually reflect really is more their compositions. For example, the black ones have a whole lot of titanium in them. But what those compositions in turn reflect is the different regions within the lunar interior from which they were generated. And so people like me who do experiments in the laboratory try to recreate what that internal structure is by looking at these various pieces.
You know, today here on the Earth, when we look at volcanoes, they all have these big calderas, so the material bubbles up and then forms what looks like a crater. But when we look at the moon and we call these craters impact craters, are there any volcanic caldera?
Yeah, there sure are. And there are a number of vent locations, places where we can really see this is where the eruption started, and this is where the lava flow began. And we can see piles of this, what we call pyroclastic material, these glass beads and other things that came out in these fire fountain eruptions. So yeah, they're out there. In fact, Apollo 16 was chosen to go to a place where they thought they were going to find a whole lot of these kinds of lava domes. Turned out not to be the case, unfortunately, but that's why they went there.
Well, are they active today, or has the moon cooled off and at the point where it's really waning?
Yeah, the moon has not had really voluminous volcanism for at least the last billion years. However, there are some new observations from the Lunar Reconnaissance Orbiter that are at least suggestive there might be a couple of places that were a lot younger. If that's true, and that needs to be confirmed, the jury is still out, that would be a really game-changing observation for how we think the moon works.
You know, I get questions all the time from many people in the public about humans versus robots for space exploration. So what's the point of sending humans to the moon when we could send robots, and we can do that cheaper, and we don't have to risk human life? Is there huge scientific benefit for humans in the loop?
Oh, there is absolutely. As we've talked about a couple of minutes ago, without the humans there to recognize what it was they were trying to find, it would have been dumb luck to come up with some of the answers that we now have. We humans are remarkable machines, and we are able to do things very, very quickly that a machine cannot. And so, in my opinion, the ideal is a marriage between a trained human being and a semi-autonomous robotic helper. We use the strengths of each and minimize the weaknesses of each. And so together, those things are the way that we should attack going back to the moon, particularly as we go forward in the Artemis program.
The important aspect about the Artemis program is that it's a series of missions to the moon. But what we'll learn from those, we're going to apply as we finally go to Mars.
Yeah, and I'm looking forward to that day because there are processes we know that are probably common both on the moon and on Mars. So as we first regain our space legs by living on the moon for a while, and then we jump off and go to Mars, we'll be able to test some of these very same ideas. In fact, it turns out that we think Mars also went through a magma ocean phase. But that's an idea that needs samples to be brought back from Mars the way we brought them back from the moon, from known geologic context. I can't wait.
We talk about planetary science all the time, but do we learn anything important about the Earth itself from learning about the moon?
Yeah, I want to come back to this whole giant impact idea that we mentioned at the top, and that is, if there was this huge impact, what happened to Earth? And this is how we worked out the fact that the Earth itself was completely molten.
How long did it take for the Earth to cool off?
This is one of the things that is remarkable. You'd expect that, boy, that would take a long time to cool off. But the geochemical evidence suggests that the cooling process was geologically very rapid, a few tens of millions of years. In the lifetime of a planet in geologic history of 4.6 billion years, that's not much at all. So very quickly, things cooled off. Now, the reason that this is so critical is all of this happened in the very early history of our Earth-Moon system. We have no rocks on Earth from that time, and rocks are the record books of geologic history. So we have no books from then. Only the lunar samples revealed this process. Now, if I were to tell you that the entire planet was once liquid rock, I'll bet you would say, hey, that's pretty important that we know that. And there's no way we could have known that without going to the moon. So there's one big example of a huge, important event in Earth history that we had no other way of knowing.
Well, Dave, I always like to ask my guests, what were the things that happened in their life that really got them excited about science, that really propelled them forward, that changed their direction from what they were doing into this field? Dave, what was your gravity assist?
Yeah, Jim, I think I am an outer planets mission. I have had multiple flybys, multiple gravity assists in my career. I've been very fortunate. The first one, of course, was the Apollo program. I was 9 years old when Apollo 11 landed, and I'll never, ever forget watching those missions. And as I was growing up, I was a total space geek. I was eating, drinking, breathing the space program every day. So that was one that really fired me up. The next one was the eruption of Mount St. Helens in 1980. I was a musician. I was a music major, and I had to take a science course just to check a box. I was taking this earth science course that we were talking about volcanoes, and we were watching as St. Helens was getting ready to blow up. And when it did, oh my goodness, that just absolutely totally changed my trajectory forever. I said, this is what I want to do. And off I went. And then the third thing is I've had the great fortune to have had a number of excellent mentors who have taken me under their wing and helped me understand that, if you want to do things that help understand the solar system and planetary science, here's the way you go about doing that. And I'll be forever grateful for the opportunities that I've had. And one of the things I like to do, if I can, is help create as many of those opportunities as I can for the next generations that are coming up behind us.
Yeah, I agree. I understand. It's really important that we talk about the science that we're doing and let the public in on all the secrets we're finding. Well, Dave, it's just been a delight chatting with you. I really appreciate your time to come down and give us the really explosive truth on volcanic and magma oceans that we've learned about from the moon.
Thanks, Jim. It's been a great pleasure talking with you this morning.
Well, join me next time as we continue our exploration of the moon. I'm Jim Green, and this is your Gravity Assist.